Hello and welcome to section 15.2 on line integrals. The first type of line integral we're going to consider known as scalar line integrals. And so to motivate the idea for this type of integral, let's consider a fence in this shape here where the top is given by this orange curve here and the bottom is given by this blue curve here. Okay, and I'll denote this base curve in the xy plane as C. In this top curve here, okay, I'll write this as z equals f of x, y, which we usually think of, right, as a defining a surface. Well, you could just as well think about this equation as defining a surface, but we're just looking at the restriction of that surface above this blue base curve, okay? So just think about it as a certain cross section of a surface. All right, so if I want to find the area, say, of this fence, say I want to go paint the fence, I need to know the surface area of the thing. How could I go about doing that? Well, this is essentially the same question you encounter in Calc 2, except there the base of your fence is just a portion of the x-axis, right? So now we're just generalizing that a little bit and letting the base just be this curve here, C in the xy plane. But the idea, the approach is really just the same as Calc 2. Okay, we're going to first go ahead and just divide the region into a bunch of thin rectangles. And then I'm going to go ahead and chop up the curve C into a bunch of small little sub-intervals. And as long as the curve C is differentiable, if I chop these up fine enough, each one of these little pieces is essentially going to be straight. Okay, that's a consequence of differentiability, is that if you are differentiable, okay, then you're not going to have any sharp cusps in your graph. Okay, so in other words, if you zoom in far enough, okay, you're going to start to look linear. All right, so now what would be the width of one of these little intervals? Okay, well, as you can see in this little zoom in picture, okay, S here is being used to denote arc length. This width here is just a little piece of arc length, a differential arc length along our curve C. And notice that this thing, ds, is the hypotenuse, this differential right triangle whose base is dx. So we're just changing x a little bit, and then we're changing y a little bit, and that would be the height here of that triangle. And so through the Pythagorean theorem, okay, ds would be the square root of dx squared plus dy squared. Okay, now let's suppose I parameterize this curve C with this vector function r of t, whose components are x of t and y of t. And let's say t vary from a to b. So you can think you're located here at t equals a, then as you let t increase, you're going to move along the curve, and you're going to end here when t is equal to b. Well, if I differentiate my vector function, I just do that component-wise, and I'm going to get x prime of t, y prime of t. And if I take the magnitude of that thing, I get the square root of the sum of the squares of the t derivatives of x and y. All right, so now notice by doing a little rewriting here for this expression for ds, if I, a little bit tricky, but if I multiply this expression by dt over dt, and I take this dt in the denominator and I bring it into the square root, okay, then this inside can be written as dx dt squared plus dy dt squared, and that dt out here in the numerator is just going to stay there. So that's just this factor of dt you see on the right. And now this thing right here, this square root, this is just the magnitude of the derivative of our vector function r of t that's being used to describe the curve C. Okay, now also recall from Calc 3 that if I think about, say, r of t as representing position along this curve C, then r prime is really describing the velocity as we move along the curve C, and the magnitude then is describing the speed. Okay, so this is really saying what? It's saying that your differential change in distance, your ds, is equal to what? Well, your instantaneous speed times your differential change in time. So the statement that ds is really the magnitude of r prime times dt is really just going back to, hey, a small change in distance is the instantaneous speed of your particle moving along this trajectory times your little change in time. Okay, so what am I going to do with that now? Well, again, remember ds is the base of one of these little strips here that we're using to fill out the rectangular, or sorry, we're using these strips to fill out the fence, right? So now what am I going to do? Well, just again, just like you see in Calc 2, okay, over each one of these little strips, I can approximate the area of the fence over that strip, okay, by just evaluating our function at a point in that little subinterval, okay, so that'd be our f of xi star yj star, where this point here, xi star yj star, is just a sample point, so it's just some point in that little interval. And then you're going to multiply that height with the base, which is, at least for a finite step, we would denote as delta s. Okay, and so then if I add up a bunch of approximating rectangles like this, I'll get an approximation to the area of our fence. And then, of course, taking a limit as we let the number of subdivisions approach infinity, we'll get the exact value of the area, which we will write notationally as the integral, and then you see this little subscript c. This is just saying we're going to integrate our function f over c, and notice here the differential is ds, okay, which is again is denoting this little change in arc length as we move along our curve c. Now, how do we actually go about computing that? Well, f, right, our function here along this orange curve, right, we're gonna just feed the function f the components of our vector function r, right, because these component functions describe the points along C, and I want to evaluate this function f at those points. So I'm going to just take f of x of t, comma y of t, and then my ds, as we argued down here, is just the speed times time, right? So in other words, it's the magnitude of the derivative of the vector function that describes C, and then you have your dt. Okay, so then lastly, what I want to mention here in this video is just really the definition of a line integral in more generality. So if I have a function of two variables, okay, the line integral of that function over a plane curve, so that's just like what we were looking at in the last slide. So if your plane curve is defined by these by this vector function whose components are x of t, y of t, then to compute this integral, again, you're just going to evaluate your function at those component functions, and then your ds is just going to be this speed times time, and you're letting t vary from a to b. All right. Now, if you have a function for three variables, okay, then you're going to integrate that thing over a space curve c, and we'll see some examples of this in the next video. And there, yeah, now you're going to have x, a y, and a z of t as you move along some space curve, and then you're going to integrate in much the same way. Okay. All right, so in the next video, we'll look at problem 1 on the worksheet to illustrate all of this. All right, thanks.